I always like to look at the same problem in different ways, because sometimes by looking at it just a little bit differently, you gain a new insight. So, if you look at the Gram Schmidt orthogonalization process, then what you notice is that really the span of A0 is the same as the span of Q0. Why? They point in the same direction. The span of A0 and A1 is the same as Q0 and Q1. Why? Because you computed Q1 by taking A1, subtracting out the component in the direction of Q0, and then making it of length 1. And in the same way, you can conclude that the span of Q0 is the same as the span of A0. The span of Q0, Q1 is the same as the span of A0, A1, and so forth. And this is just a property of the Gram Schmidt orthogonalization process. So, in general, you can say, well, by the time you reach the column indexed with k, and you want to compute the q indexed with k, vector q indexed with k, you already have computed all of the prior vectors q0 through k minus 1 from vectors a0 through ak minus 1. So you know that ak must be a linear combination of q0 through qk because it lies in the span of those vectors. So, AK can be written as a linear combination of Q0 through QK minus 1, plus rho KK times QK, right? Obviously, I picked how I chose to label my coefficients carefully. If I now take the dot product of Q0 with AK, then that's the same as propagating that in and distributing it, and therefore I get Q0 transpose here, Q0 Hermitian transpose here, Q0 Hermitian transpose here, and Q0 Hermitian transpose here. What I find is that this is equal to 1, because these vectors are mutually orthonormal, and all of these dot products are equal to 0, so they disappear. So what you get is that rho 0k can be computed by taking the dot product of Q0, which we already know, with the current vector AK. Right? That follows exactly the Gram Schmidt process that we outlined right here if we had carried it through to the step where we were working with vector AK. So what we conclude is that rho 0k is just the dot product of A0 of Q0 with AK. Well, then we can go and take the dot product with Q1 and propagate that through. All of the terms, except for the one that involves Q1, disappear. And we conclude that rho 1k is equal to Q1 dot product with AK. And obviously this is true in general. So, we know how to compute all of these coefficients right here. Right? Now, we can go back and say, let's go back to how AK was given as a linear combination of the vectors Q0 through Qk. So we're back here. And we can then say, oh, but what we can do is we can subtract out from both sides these terms and leave that one on the right hand side. And what do we get here? We get the component of AK perpendicular, orthogonal, to vectors Q0 through Qk minus 1. Okay? After that, we know that Qk must lie in the same direction as AK perpendicular, but it must be of length 1, and that tells us that we can choose rho kk to be the length of AK perpendicular. So this is an alternative way of arriving at the exact same algorithm that we know as the Gram Schmidt orthogonalization process or method. And what it really captures is the fact that AK can be written as a linear combination of vectors Q0 through Qk.